Hey everyone, welcome back. Today I'm joined again by Aaron, and we're gonna chat about Avalanche warp messaging. So, Aaron, let's start kind of like understanding Avalanche warp messaging with the P chain. What is the P chain's role in this whole construct?
So the P chain fills the one thing that we have, fills the role of the one thing that we haven't talked about yet, which is this main question, which is if I'm going to generate a private key and public key, and you want to verify some signature, how do you know that that is a private key that you care about whatsoever? I can send you some signature. I can generate a private key at will. I can generate a new key pair at will. So how do you know that it's actually comes from me? And how do you prove that to anybody else? Because if you can't answer that question, then the entire process is worthless. And so what the P chain does is it plays the role of what's typically called the public key infrastructure. So oftentimes, if there's two people that are communicating, there might be some sort of key exchange. And in some larger, broader context, there might be a broader distributed system where there's somebody plays the role of providing this. This is the actual public key registered to this other party. So you can think about DNS as one example, where there is some set of parties that are saying, yes, this key actually belongs to this specific domain. If you receive a message that has been signed correctly, you can actually verify it against here. And they provide that sort of public key infrastructure to say, you are actually talking to google.com right now. And so what we use the P chain for is to play a very similar role, which is that I can actually register my public key to the P chain. And so what I actually will do is do this when I'm registering a validator to the P chain. So you don't have to worry about this too much right now if the validator is a foreign concept to you. But the important thing is that when you actually want to verify some signature coming from a validator, you can actually resort back to the P chain to see what is the BLS public key. And these public keys are registered for a long time, essentially to form the backbone of this public key infrastructure, so that me sending you a signature is not some meaningless message, but is actually tied directly to me as a validator.
Cool. And when we talk about the warp messages, right, like it includes some properties, right? And one of them is the source chain ID, right? So why does a warp message need the source chain ID? And maybe even going further, why doesn't it have a destination chain ID, right?
That's a great question. So the source chain ID is that you know who is intended to have signed this message. So when we talked a bit before, we talked about how there might be 1,000 different public keys that you want to verify have all signed some message. In that case, you might be able to pre-compute the aggregated public key of all of those people that you care about. In the case of a Byzantine fault-tolerant network or a blockchain system, as we typically are going to be talking about, there might actually be some validators set where any number of validators, and we don't know who, will be failed, crashed, faulty at any one given point in time. You could pre-compute the public key that corresponds to all 100 of those validators, but if one of them is missing, as could very possibly happen under a BFT system, since it could simply be crashed, then if I take only 99 of those signatures, which I might want to cause to result in a correct value, then it might not actually be verified against that same signature. And so what we use the source chain ID is to play two roles. One is to say, this is the validator set, or oh, this is the blockchain ID that purports to have signed this message. And two is to use that as the lookup. So when I send you Avalanche warp message, including the source chain ID, you can say, okay, well, the subnet that this is coming from has this validator set. So in addition to the source chain ID, what we also include in the signature scheme of this is we include a small bit set that says which validators in the validator set actually have a signature that's included. So instead of requiring all 100 validators to assign a message, we can actually say, well, we use this bit set to say exactly which validators out of that 100 sign the message. And so by doing that, we can take, let's say, 67 of those validators and say, these are the 67 that we expect to have a signature included in them. And what we can do then is we can say, okay, well, we'll combine just those public keys on demand in order to find this is the exact public key we want to verify this signature against. So the source chain ID plays this important role of saying, where do we go in order to figure out what signatures are expected to be included in this message? And how do we verify it? From a functional perspective, it also plays the role of adding semantic detail to what this message is saying. It says, not that this message came from anywhere, not that this message came from Bitcoin, but this is the chain where it actually came from.
Yeah, that makes sense. So let's talk about the flow of a message, right? Like, so we have a subnet where it originates, and then we have this AWM relayer who's doing some work. And yeah, maybe you can talk about kind of like the first thing, like what happens, what's the role of the relayer at all, and what happens when we send a message?
Sure. So the way that this works in Avalanche warp messaging is first, the blockchain decides this is a message that I'm willing to sign. And the way that happens is there's two different types of messages that a chain will sign, at least from the perspective of the EVM. That is whether a user specifically calls the word precompile to say, I want to send message A to this to someplace. And so that caller or that user can specify exactly what that message should be. And the blockchain will basically construct some message that is willing to sign from then on saying, I, this source chain, am willing to sign this message that was resulted from a call from this address. And so those are the two pieces of information that you might want to verify, which is what source chain does it come from? And on that source chain, who is the user, the caller that asked for this message to be sent? So those are the two pieces of information. And separately, we also might have, as soon as a block is accepted, all of the validators of that chain should be willing to sign that block hash to say, this block hash, all of it, the details included in it, and recursively all of its parents, the entire blockchain that comes before it, are now proven by this validator set to say, this is actually occurred. And so once those messages are willing, the validators are willing to sign those messages, it's up to a relayer to actually aggregate signatures from all of the validators of that network. So the relayer might observe these logs or this block that ends up getting accepted by the network, and then go and say, I'm actually going to request a signature from each of the individual validators of that network. And as soon as I see, let's say the block has been accepted, I can say, well, there's 100 validators in this network. So I'm going to request a signature of that block hash from all of these validators. And as soon as I get back the required threshold, which by default is going to be 67 of them, I'm going to say, well, that's all that I need. So I can take an aggregate of those signatures, construct the bit set, and construct the entire warp message that I've received from them along with this signature, and then send it to whatever destination I want. And on the destination side, they can then look up based off of the source chain ID and verify that signature that came from the source chain.
Cool. So how does that look in practice? So the relayer then just issues a transaction on the destination chain?
Yep, that's exactly right.
Cool. So in order to be able to submit a transaction, it actually needs a wallet with a private key on that destination chain and even gas tokens, right?
Yep, that's exactly right. That's what makes having a relayer fulfill that role nice, is that we don't necessarily want to have a private key that's managed by each individual validator with the ability to sign transactions. We want to abstract that away, move it someplace else. And these relayers are easily incentivized by saying, well, you can actually collect some reward if you deliver this message in some way, shape, or form. Or you could even run this as a service for any of the users of either the destination chain or the source chain in order to facilitate actually delivering those messages to the destination.
Yeah. So let's think a little bit about load, right? Like a large number of messages now travels through the Avalanche network. What is kind of the heavy, where's the heavy lifting happening? What's kind of the load on the source chain, on the relayer, and on the destination chain validators?
Yeah. So the heaviest load is most likely going to be on the relayer. So as messages get accepted or people are willing to sign messages, there's no actual additional load that really comes out of the EVM on the source chain. All the source chain is doing is processing transactions and processing blocks as normal. The additional thing that gets emitted is just a log event, which we charge for in the exact same way as any other smart contract on the EVM. There's very, very little additional cost on the source chain until the relayer steps in. So as soon as the relayer steps in, it will actually ask for signatures from each of those validators on the source chain. And this is a fairly small cost to pay to just check if that message is valid, check if it's in its database, and if so, construct a signature and send it back to the relayer. So if there's multiple relayers that are trying to do this at the same time, there may be some wasted work, but if there's only one relayer, as there will most likely be in a lot of cases, then what will happen is that relayer will send this request to all of the validators. It will then aggregate the signature and send it to the destination chain. On the destination chain side, the heaviest piece of work is actually going to be processing that message and actually validating that signature. So the one piece of work on the destination side that is going to be O of N, or scaled in the size of the number of validators on the source chain, is actually aggregating the public keys. So it's actually not the number of validators in the source chain, but the total number of validators whose signature is included, because they'll have to look up the validator set of that source chain, check the bit set to see which validators are purported to have been included, and then aggregate those public keys and actually validate a signature against that. Validating the signature is incredibly cheap. Validating the signatures is also very, very cheap, but that is the one piece that will end up being an O of N piece of communication.
Okay. And let's think a little bit about trust here, right? Like, so usually when we have cross-chain communication, many protocols work with like a trusted third party, bridge wardens, bridge validators, however you want to call them. How does that work in Avalanche warp messaging?
So typically, if you want to have some trusted third party, that means that you're going to rely on somebody that is using a lower trust assumption than what the two blockchains are already using. And so that might look like some five-party multisig that's saying, I observed this happen on chain A. You have no better way to verify that that happened on chain B. So we use this trusted third party. And then they sign a message saying, well, all five of us observed it on chain A. Therefore, we'll actually take this action. What we do with Warp in order to have the best possible trust assumptions is we actually say that we're going to, well, actually, we leave this to be configurable, but we require that it's 2/3 of the network to sign it by default. And it could actually only be 1/3 as well. But the purpose of this is we make sure that a sufficient portion of the network has signed the message such that if that same portion, so the goal here is if a super majority of the network on the source chain has signed a message, then if that amount of the network were corrupted, the source chain would be corrupted anyways. So essentially, if you observe a signature that has a super majority of stake that has signed it, or technically even less, then if that message was forged or that message was created by some Byzantine set of validators such that it didn't actually occur, then that source chain has already been corrupted by that Byzantine set of validators. And so what this means is that there's no real change in the trust assumption. You get the minimum security of one of the two chains that are communicating with each other. For this destination chain, it can't actually get any better security than that validating the validator set from the source chain produce something correctly. Because if that blockchain were already corrupted or already majority Byzantine, there's nothing that it could do, really.
I see. Cool. Perfect. Thank you very much. And yeah, thanks for joining us today. See you soon.
Thanks, Martin. See you soon. Bye.